So let me start with a simple question. Could you provide an intuitive explanation of the gauge-gravity duality and its significance in modern theoretical physics?
So gauge-gravity duality is basically a relation between a quantum gravitational system and a quantum many-body system without gravity. And just even from the name, that somehow you have a quantum gravity to be equivalent to a quantum many-body system without gravity already suggests that this is something profound. And on the one hand, even though quantum many-body systems are generally very complicated, etc., but we understand, we don't have any conceptual, we understand its foundation very well. Okay, just quantum mechanics, just large number of degrees of freedom. And so we understand its basic foundation very well. But the foundation of quantum gravity, we currently don't have. So this is a wonderful framework so that we can use something which is already conceptually well understood to probe the conceptual questions, in particular foundational questions of quantum gravity. And so this is one aspect which is remarkable. And another aspect which is remarkable is that we also know that quantum many-body systems are in general very complicated. They have very rich dynamical behavior, many emergent phenomena, etc. And so it turns out we can actually use classical gravity to understand many of such, say, emergent phenomena or strongly dynamical phenomena for these quantum many-body systems. So the duality goes both ways. Yeah.
So the holographic principle involves the idea of geometrizing the renormalization group flow. Could you explain this concept and why is the AdS CFT, why these two terms are central to this duality?
Yeah, so even from our ordinary physical experiences, one of the fundamental principle is physics at very largely separated scales. They are more or less independent of each other. For example, atomic motion is independent how the Earth goes around the sun, and how the car moves is also independent how the Earth goes around the sun. So physics at all these very widely separated scales, they're more or less independent of each other. And so even though this has been recognized, for people for many generations, thermalization group is a way to formalize it into a general principle. Say, using the thermalization group, you can really understand why physics at such distinct separated scales, they don't say strongly correlate with each other. And so what this holography does is somehow make this notion of separation of scales geometric. Say, we know that if from ordinary physics, we know if something happens, say in Boston, or something happens in Columbus, that normally they don't have anything to do with each other because they're widely separated in space. And so holography tends into this kind of non-correlation in space and non-correlation in scale, essentially equates them. And so this non-correlation in scale in this quantum many-body system then become non-correlation space in quantum gravity. Yeah. So this quantum gravity essentially has one more dimension, and this dimension essentially is the dimension of the scale of this quantum many-body system. And so our two usual notions of this not correlated for widely separated scale, they just become the same thing. Yeah. Yeah, you can also just intuitively understand this will help. This is essential to the duality. It's because because first this principle helps us to understand this extra dimension in gravity, and so this is on the one hand, and on the other hand, this provides a very geometric way to understand the separation of scales. And because separation of scales has always been a little bit abstract, even though we intuitively understand, but to formulate them, say, as mathematical principles is actually not that easy. So that's why we have this kind of framework of of thermalization group, etc. But to formulate it into a geometrical concept, then it's much easier. Yeah.
Then, given that this duality seems to pertain to AdS space-times, why is the physics community so fascinated by it? Well, we know that our universe is nearly flat. So can we make predictions about our universe using this duality?
So the reason we are still fascinated about it, even say 30 years or almost 30 years after its discovery, is that this duality gives us really a first glimpse of what quantum gravity is like. So previously, our approach to quantum gravity has always been a little bit semi-classical. And so either semi-classical or using string theory, even though provides a consistent, say, theory of quantum gravity, but string theory is intrinsically perturbative. And you cannot really probe those strong quantum gravitational regime using string theory, at least not from current techniques. And but this duality really gives us a first example, which we can actually define quantum gravity non-perturbatively, not based on, say, small G Newton expansion, etc. And so that's why this is very valuable. And also the reason is that this duality gives us such a rich structure, even though after almost 30 years, I think understanding is still, in a sense, at infancy. So there are still many fundamental questions we don't understand about the quantum gravity we can learn from this duality. And once we really thoroughly understand this duality, and then understanding flat space-time or de Sitter, then it's not that should not be that difficult. And so that's why we need to, just say, so this is just the normal practice in physics. Say, when we say have harmonic oscillator, and then we would like to understand harmonic oscillator from all possible perspectives to beat it to death. And then once you have fully understood harmonic oscillator, then you see harmonic oscillator is everywhere. Okay, then you find it exactly applies everywhere. So somehow we need to understand this AdS really thoroughly, and then we presumably then we can understand the theta of flat space-time.
Very well. So holography has offered us valuable insights into the black hole information paradox. In your view, what do you consider to be the most natural resolution to this paradox?
So this paradox, of course, can be formulated at many different levels, and also different level of sophistications, etc. I think so far all the evidences point to that even when you include black holes in quantum gravity, our usual notions of quantum mechanics, like unitarity, those things, they should still survive. They're not breaking down due to the presence of black holes. But black holes do bring a lot of exotic physics, which is unintuitive and unconventional from our normal semi-classical, say, effective field theory perspective. So that's why this paradox is so fascinating. And it tells us somehow quantum gravity is not just, say, some physics at Planck scale, say very short distances, but actually have some manifestation at very large distances, and in terms of the black hole physics, etc. And right, so so I think that's the most natural resolution. So I think firewalls, I think now we understand this question much better. So in the sense we believe, at least for say black hole formed from gravitational collapse, likely there's no firewall. But if you just give me a generic state, say in your quantum gravitational system, and that state may have a firewall. And so really depend on the context you ask your questions, and that context is very important. Yeah, so in the sense whether you have a firewall or not depend on the history of your states. Yeah, and so I think that's our at least my current understanding at the moment. And so regarding the fastball proposal, of course, the fastball proposal is a very intriguing idea, and it's not only, I think its value is not only say, even though it's originally aimed at, say, yeah, it's motivated by black hole information paradox, etc., and also provides very interesting perspective on the black hole paradox. And it also gives us many other things, say, new ideas for finding new solutions, etc. Yeah. So first of all, I think it's not contradictory with the idea that the evolution of black hole is unitary. It's just related to the specific ways to understand why it's unitary, etc. And so the island has received some very important support, say, from holographic systems. And so we believe islands should be part of the story. And that's why, that's just one aspect of the black hole physics is so exotic, somehow because they give you, at the macroscopic distances, they give you a very unintuitive physics, which you cannot understand using the normal framework, say, of effective field theory. Yeah. And the remnants, we don't really have much support for it right now. It's a logic possibility. We cannot rule it out. And but we also don't see, at least we are not forced to have it at the moment. And remnant is a regime we cannot directly probe. And but it does exist as a logical possibility. Yeah.
Okay, so your research has extensively focused on entanglement entropy. Could you explain the current understanding of entanglement entropy through the lens of holographic principle? And how does this differ from the traditional quantum mechanical perspective on entanglement entropy?
Good. So entanglement entropy is a very useful quantity because it quantifies how systems are entangled, say how different parts of the system are entangled with each other. And so it's a very valuable quantity because it gives a very quantitative measure. And so in the sense that the entanglement entropy for holographic systems and holography for traditional quantum mechanical systems, they're not really different. They're really the same thing because entanglement entropies are just some numbers which tell you, say, how different parts of the system are entangled. So what's actually much more fundamental than entanglement entropy itself is the structure of entanglement. Say whether you have bipartite entanglement or multipartite entanglement, or even within the bipartite entanglement, when your system have infinite number of degrees of freedom, then they can have different kind of entanglement structure. And so those kind of things often cannot be just captured by entanglement entropy. So you have to go to some deeper structure to see those entanglement structure. For example, by looking at the algebraic structure, by looking at the, these kind of things. Yeah, so I would say in holographic context, entanglement does play a crucial role, which is different from the usual context. Yeah, not entanglement entropy, just entanglement itself. And in the sense that now we believe that space-time actually emerges from certain kind of entanglement structure. And so the space-time itself maybe can be viewed as a manifestation of certain underlying entanglement structure. And so to understand what kind of entanglement structure which give rise to space-time, etc. So that's one of the outstanding questions so people are exploring right now. Yeah.
All right. So in your paper with S. Josephine Su, you introduced the concept of entanglement tsunami, which is related to the thermalization in strongly coupled quantum field theories. How does holography enhance our understanding of thermalization processes, and what insights have emerged about the dynamics of quantum systems from these studies?
Yeah, so let me just first say a few words regarding the thermalization itself. Thermalization, of course, is a familiar phenomenon which we observe every day in our life. And but understanding how quantum system, say general quantum systems thermalize, are really very complicated dynamical questions. And in particular, this also become very important because now you can actually probe thermalization process in the lab, quantum many-body system in a controlled way. So you can actually do experiment to test various kind of summarization, etc. Yeah, whether system summarize or not. Anyway, and again, entanglement provides a very important perspective on how a system summarize. So we ask why a system summarize, and what's the underlying physics for that, and the slogan now we can give to this question, why a quantum system summarize, is that somehow as time evolves, generically the system become more and more entangled. And when system become more and more entangled, a macroscopic manifestation of that is summarization. And so say when any part of the system is highly entangled for the rest part of the system, and if you only can probe only this small part of the system, then you don't have information of the rest of the system, and then essentially you look like you're looking at the thermal state. And so the summarization, so now it can be just understood as a way which the system become more and more entangled. And so what holographic tells us is that if you try to look at how the system become more and more entangled during, say, time evolution, you find actually the process can actually be described by some very simple rules. For example, if you just look at entanglement entropy between different parts of the system, then you find that the entanglement entropy grows linearly with time. It's very, very simple, a very simple rule. And naively, if you have not done such calculations, you would expect anything can happen. It would be very complicated. Yeah, why should be linear? But turns out it's a very simple linear rule. So that's one of the thing which holograph help us. So that's one of the first calculations, say, of this kind of entanglement growth in higher dimensions. So in 1+1 dimensions, you can use very special techniques of CFT, two-dimensional CFT, to calculate this linear behavior. But people didn't know whether this linear behavior is general or special to 2D CFT, etc. But then this holographic calculation tells us that this is actually generic in higher dimension. And not only generic in higher dimension, but actually give us a new way to quantify how systems summarize. And then you find that this, if I tell you that this entanglement grows linear with time, then a very larger question then you ask is that what is the slope of this linear growth? And what's the physical meaning of this slope? And it turns out actually the slope is something you can actually calculate and actually assign a physical meaning. It's like this slope is like a velocity. And it's like how it can give you a quantitative way to understand how entanglement actually spreads in space. And yeah, and so that's this concept of entanglement tsunami, is that this slope of the increase can actually be understood as something propagating in space-time. And this slope can be understood as the velocity of the entanglement propagation. Yeah, and more generally, holography can provide as I mentioned, the summarization is a very complicated process. It's very hard to do calculations for general quantum many-body systems. But with the help of gravity, we can actually turn, with the help of holography, we can turn these many questions of summarization into a numerical gravity calculations. And even the numerical gravity calculations are still complicated, but they're well-defined questions, which we can actually do. And you just solve some partial differential equations. And so many insight has been obtained on how systems, say strongly coupled systems, summarize, which we would have otherwise have no really tools to do any calculation. So, for example, we have found that the strongly coupled system can summarize in a very short time scale. So holography tell us what are the typical time scales for system to summarize. And also, tell us when the hydrodynamics will sink. Yeah, so when systems summarize, then at a certain stage, you will be able to describe the system using hydrodynamics. And the holography tells us when does the hydrodynamics start applying, etc. It turns out that the hydrodynamics start applying much earlier than people anticipated from general principle. Yeah, so these are the deep insight which we learned from the holographic calculations.
Very interesting. So going back to our discussion of the emergence of space and time, in your recent paper with Samuel Luthuser, you discussed the emergence of space and time in holography. Could you briefly explain how this occurs and whether these ideas can help us address the long-standing problem of the arrow of time?
Yeah, so the basic idea of what we Sam and I have been doing can be formulated as this statement we call the subregion subalgebra duality. So just let's consider, say you have this duality, you have this holographic duality, you have this a quantum gravitational system due to some quantum many-body system. And so we'd like to understand where do those space-time structure in this quantum gravitational system arise from this quantum many-body system. And so this subregion subalgebra duality is a way to understand it. It's a new framework we proposed to understand it. And the basic idea is the following. Just look at any space-time region, say on the gravity side. And if you say, you have many ways to think about the space-time region, say in gravity. Say if you have a space-time region, there's a space-time structure associated with it. There's a causal structure. And also you can consider degrees of freedom in this space-time region, and you can do experiments there within the region, etc. So the basic idea of this subregion subalgebra duality is everything about the subregion on the gravity side is actually described by some abstract algebra on the quantum many-body theory side. And so all the physical operations within the region entanglement structure, you can actually describe it using some kind of abstract, using a kind of abstract algebra. And so this is a very powerful framework. And this also generalized this so-called notion, so-called Gelfand duality mathematics. So one of the conceptual revolution in understand space in mathematics is this Gelfand duality, which is the statement. Say if you want to describe a topological space, rather than describe the open set of that space, different regions, open sets of that space, alternatively, you can just look at all functions defined on that space. Just look at all possible functions defined on that space. Turns out that the structure of the algebra of all functions encode all the geometric structure of the space. So this is called a Gelfand duality. And this is a really revolutionary idea. And because now you can generalize the concept of the space. Say, so now you say if we look at the algebra of functions, okay, and that tells us the topological space. And then you can look at some other algebra. Yeah, say if you look at, then you can look at some, the algebra of functions are commutative. But now you can consider some non-commutative algebras. It turns out that can be used to define some non-commutative space and to define the whole notion of the non-commutative geometry, which you cannot define using the normal geometric concept. And so this subregion subalgebra duality, which we propose in this holographic context, is like a generalization of this. It's that this space-time region in the block can be actually described by some abstract algebra in the field theory side. And this abstract algebra just can be used to understand all the geometric and the physical operations. I was just saying that this there are various exotic kind of some simple examples of this kind of non-commutative space. For example, certain kind of fractals and a certain kind of space you define using some kind of non-ergodic foliations. And say, for example, if you just look at on the torus, you do a motion which is not commensurate with the sides of the torus, and then this one-dimensional curve will eventually fill the torus. And how do you define? How do you define the space of this one-dimensional curve, etc.? So these kind of questions, which we don't know how to define them using conventional notion of topological space, but then using the algebra, you can actually make sense of such space and study the geometry of such space, etc., using this non-commutative geometry. So this is the concept of non-commutative geometry.
Very interesting. All right, so moving on. So while string theory has provided us a rich framework for theoretical exploration, its connection to the real world is still a subject of debate. How do you see the role of string theory and holography in addressing real-world physical phenomena, particularly in the areas like condensed matter physics?
Mostly string theory and holography for long have mostly been, in a sense, it's an intellectual framework for us to explore quantum gravity. It's more like, as I mentioned, it's more like the harmonic oscillator, but somehow you haven't defined the real life version of this harmonic oscillator. And so they give us lots of insights into the structure of quantum gravity. And as I also mentioned, they give us a lot of new insight into dynamics of quantum many-body systems, which are of strong interest to condensed matter systems, etc. And so it's a very interesting framework because it does not correspond to anything specific in nature right now, but somehow it gives us lots of insights. So I would phrase it more as a conceptual framework.
So, looking ahead, what are the primary directions for your research in the next 5 years? And are there some specific questions or areas that you aim to explore further?
My research has been mostly devoted into 3 different areas, but they are also interconnected. So one area, say, for the last few years has been using these operator algebras to understand the entanglement structure, say, of a quantum many-body system, and then to understand the emergence of the space-time in the bulk using holography. And so I think this is a very promising direction for understanding the general structure of quantum gravity. So this also has the potential, maybe we can, using this algebraic language, to generalize holography, say, to a asymptotically flat space-time or to de Sitter, etc. And so this is certainly a direction I would like to explore, say, in the near future. And another direction which I have been pursuing during the last number of years is to develop new formulations of hydrodynamics. So maybe 6 years ago, we developed a new formulation of hydrodynamics as a universal effective field theory for general quantum system. And so that provides, say, an action principle. So that provides a way to formulate hydrodynamics just based on action principle and the symmetries. And so this is very valuable in the sense it's this is valuable in several aspects. So first is of course can help us. One way is that this can help us understand hydrodynamic fluctuations, which traditional way cannot do, and also this can help us to write down hydrodynamics for new exotic systems. And one thing we have been doing, for example, we have written down hydrodynamics for quantum chaotic systems. We also have written down new formulations of magnetohydrodynamics in the strong magnetic field region. And so that can have applications, say, to neutron star physics, etc. And also, I believe this hydrodynamic, new ways to thinking about hydrodynamics can also help us understand quantum gravity, certain questions in gravity. For example, the entropy, etc. Just where the gravitational entropy come from. For example, now we believe you can actually associate gravitational entropy for any surface, say in gravity, and that's where this kind of concept come from, etc. I believe this kind of hydrodynamic thinking can help understand such question too. And a third direction which I pursued during I've been pursuing during the last few years is to understand the thermalization process using entanglement and understand how entanglement grow, spread during the thermalization, etc. So there's also rich physics there and deeply connected with holography, black holes, etc.
Thank you so much for this insightful discussion. And lastly, what piece of advice would you offer to aspiring physicists and researchers in our field?
I think this is an interesting time in our field. It's because the field is diverging in many directions. So it's not like at some point, say, most people in the field working on similar things. And right now, the field is very, it's going in many different directions. And so I think this is a very exciting, so that means that there's many directions one can explore. And so you can just pick because you have many choices, and if one type of problem you don't like, you can always find some other type of problems. So in principle, there are many choices in terms of the style and in terms of the nature of the questions, etc. And yes, I think this is good news for beginner students, because if everybody works on the same thing, and then say if you are interested in quantum gravity, but then if these are only topics you have to work on, and then you're not that interested, then it's not very good. And but of course, on the other hand, to have so many different directions right now can also be overwhelming for beginner students. And you may say, oh, there's so many different things, maybe so many things I have to learn, etc. But I would say just don't worry. And I think for beginner students, a key thing is to go deep in one subject. So if you go deep in one subject, become expert in that subject, then branching into other subjects or other topics and directions become much, much easier. And once you have developed, say, the maturity and developed going deep into a single subject helps to develop your maturity. And once you have that level of maturity, going to more directions, more subjects, learning other things become much easier. Yeah, and you also have more confidence. Say if you just work on one subject, you become the expert in that subject, and then people say famous physicists want to know that subject, they will go to you. And then that is a great way to boost your confidence. And then when you have this kind of confidence, then that helps you to go into other fields and go to branch yourself. And yeah.